Hey everybody, how you going? Just gonna get started in a minute. Oh, I'm on the wrong team. I've got a lot of teams now in my Microsoft Teams. I just have to make sure I've highlighted the correct part. Oh yeah, it looks like I'm live on streams. That's good. On Restream, I seem to be going okay. Cool. Just make sure I've got my chat available. Okay, welcome to week 8, folks. So great to be back for another exciting week of COMP2300. We're diving into a topic which is probably complex, or the most complex topic which we look at, specifically related to your disco boards now. So we've been working our way, building up more and more kind of facility with the basic building blocks of how to use a computer on a disco board. So some of that would be how to do little bits of arithmetic, how to do some control flow, how to make functions, how to do loops, how to use memory properly, using data structures in memory. And now all of these things, which I guess were the basics of something like COMP2300, where you learned how to do them in a high level language. Now you know how these things work on the disco board, and you know how they really get implemented when you write a program in Java, for instance, or you have some idea about how it might really be implemented on the CPU itself. And now the difference this week is that we go into some topics of things which you probably have never touched in Java or a high level programming language. So they're programming paradigms or computing paradigms which you probably haven't looked at already, or if you have, you might have just sort of scratched the surface. And now we're going to scratch the surface a little bit more and see how they're kind of crucial for how computers work. And the two topics which we're going to look at this week, the first one is called interrupts, and the second one is asynchronism. And both of these topics are related to times where you as a programmer are not in control. So we'll see, I'll explain what I mean when we get through this lecture, but I guess one more general note, I like to think of COMP2300 as a course where we break everybody's magic wands, right? So you can think of computer programming, right, like sort of like magic in Harry Potter, right? You get a wand, you get to your laptop and your editor, you open it up, and if you know the magic words, then you can get your computer to do really cool stuff, right? You can type 4, open curly bracket, I = 0, I <10, I++, and you know what's going to happen. You've got these magic words. And it's just the same as saying Wingardium Leviosa, right? And something magically rises up. And then what we do in COMP2300 is we show that all of your magic words are just like big cogs in this big clockwork mechanism, and all the way down there, it's all connected to each other. It has a principle behind it. In Harry Potter, the magic doesn't have any principle behind it. It just is in the universe. If you say Wingardium Leviosa, things rise up. That's how the universe is. In computers, when you type in the words in your high-level programming language, there's no magic. There's a logical sequence of principles that mean that a certain sequence of events take place, going down to little wires inside your CPU with voltages that are 5 volts or 0 volts. So it's something which is completely explainable, and I hope that that's that's something that you're getting the picture of in our course so far. A few admin notes before we start. I had a bit of a discussion about this with the tutors last night, that we're coming up to when everyone's delivering assignment 2, and I can see that there's wonderful work going on in that in the Piazza. We also have our eyes on the horizon to when assignment 3 will be due, which is just at the end of the semester. And I think, as I've said several times so far, to complete assignment 3, which is actually available on the website, you can't get the template right now, but you can certainly look at the assignment and think about how you would do it. To do assignment 3, you need some of these little wires. And I might make myself small. I've got a remote control now, so I can go to small mode. You need these little wires to plug into your disco board, right? Your disco board's got all these little pins on it. And if you don't have the little wires, you can't do assignment 3. And unfortunately, it has to be your responsibility to get these wires. So I really want everybody to think, first of all, do you have wires? And if you don't have wires, order them. And please order them today. Because I just don't want to be in situations where people are telling me, oh, I ordered my wires a week ago and they didn't show up, and now there's only a week left to the assignment. What on earth am I going to do? Because if that happens too many times, we won't be able to do anything about it, and it will be too late. So make sure you order these before it's not too late. They're much easier to get than disco boards. They're available all over eBay, all over Taobao. You can walk into a JCar electronics store if you're here in Australia and just buy some, and they're just only a few dollars. So it's very easy to do that. Almost every website, every page in the website right now has a very big, angry, orange attention box telling you to buy little wires. It's in assignment 2. It's in lab 8. Reminder, get your jumper wires. There's a page about jumper wires, so you can see exactly what you need to get. These are the kind which I kind of recommend because they're very cheap. It's this ribbon with 40 little wires. They've all got a socket on this end and a socket on that end, and you just peel off the number you need. You really only need 3, but that bunch of 40 wires cost me $3 Australian, so it's a little bit more difficult to get 3 than 40, so you may as well just get 40. You can also find little packets of 10 wires, which are sometimes a bit more expensive. They may be higher quality. And I've got some examples of places to get them. Definitely focused on the Australian market. Of course, it would be great if I could show you things on Taobao, but coming from Australia, I can't easily look at the Taobao sellers. Most of the Taobao sellers also have sites on AliExpress, the English version, so I can see that there's lots of places to get them in China. Please order these wires as soon as possible. Make it today. Go order them right now if you're watching. If you're watching this later, make sure you pause this video and go and get them. Obtaining these is your responsibility. If you wait until the last minute, you could be disappointed, and it could cause problems with whether you can complete this course. Okay, now, where is my actual lecture? Oh yeah, here we go. Whoop. Sorry, let's get got to get all of my windows in order. Okay, now we've done the admin stuff for the day. We can start talking about some computing. Week 8, interrupts. This is the first topic. On Friday, we'll talk about asynchronism. We're going to talk a little bit about when and why interrupts might happen and what an interrupt is. We're going to talk a little bit about what happens during an interrupt and how this might work on your disco board. And then right at the end, or maybe on Friday at the start, we'll discuss how this could be related to parallel computing, parallel processing. So what's an interrupt on a computer? You know the word interrupt, like if I'm having a conversation and someone walks up and starts talking to me, that's an interrupt. And that's kind of exactly what we mean by an interrupt on a computer. So just drawing out this kind of analogy about people talking to each other. Every day we're out in the community, well, we're not at the moment, but we're somehow communicating with people, and we've got certain protocols for how we might do it. And the question I just want to pose to you, just as a thought experiment at the moment, is to think about how you handle your communications every day. So one way you might do this is maybe you would set a certain time at which you check all of your messages, and you only check that at a certain time, maybe 5 minutes after the hour, 12:05, 1:05, 2:05, you check all your messages, and then if there's anything interesting there, you handle it. Is that how it works? Generally not, right? Most of the time, you get a notification when you have a message, or your phone rings if someone wants to talk to you, or if you're walking out in the street and someone wants to get your attention, they wave at you and sort of interrupt what you're doing. So the idea of communicating does have this sense of interruptions or attention getting in some sense. And that's built into the way that we handle our everyday life. So now, just sort of moving past the communications analogy, let's think about what's going on your disco board. What's life for a disco board program? Well, we know this. We know that we've got a CPU. We know that it has a program. We know that our CPU is ticking over lines of that program. The program counter is pointing to each line. That line's getting fetched, decoded, executed by the CPU, and results happen. Tick, 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 like clockwork, right? We've talked about the clockwork analogy a lot. And the question is, how is the disco board program and the CPU going to handle communications with all of the other devices on the board, right? And this is where we get back to this slide which I showed you much earlier in the course, when we had all of these different other things on the board, right? We've got a little joystick, we've got a audio output, we've got these chips that do different things. There's ones that have like kind of a current measuring system, and ones that have serial buses for connecting different devices, and there's another USB port on the bottom there. Oh, there's the external, the one for communicating with other devices. There's the debugging one. It has to communicate with the debugger somehow as well. So we want to connect this disco board with the world. Ultimately, we want to be able to use these peripherals and somehow handle some communications. And the goal of this lecture is to start to unpack what that might mean in terms of our assumptions about how the CPU is running a program. And our assumption so far is that fetch, decode, execute ticks away like clockwork, and it never stops unless you pull the power on your disco board. And that's our assumption so far. So this lecture, we confront that assumption and break it. So time for a potentially somewhat wild analogy. I need to have some analogy time music, but I didn't get it ready for today. Maybe now I've got my little remote controller, we can implement some more OBS tricks. So imagine that your disco board is a starship, right? And you know that a starship, travels around the galaxy, explores different planets, different scenarios. The starships have many sensors. They have long-range sensors, short-range sensors. They've got some kinds of sensors which can sense life signs, and ones that can, they've got their subspace communications. Probably has some actuators as well. Of course, there's the engines in these ones. And I don't know what that does, probably something important. It may have a tractor beam, which can, whoops, I lost my, when I am in full screen mode, my, okay, I'll be in not full screen mode for drawing. And then somehow, even though it's an exploration vessel, right, we've also got our phasers, which can pew pew on people, and maybe some photon torpedoes, which can, you know, pew pew some other bad guys. Anyway, so the Starship's got inputs, sensors, outputs, actuators, and somehow it has to interact with the universe. And what is running a Starship? What is the program of a Starship? Well, obviously every Starship has a captain, right? And the captain is the program in charge. And this is assumed knowledge, okay guys? So if this is new for you, I'm gonna have to send you to Netflix for some revision. Every Starship has a captain. In this case, Captain Picard. Now, how does Captain Picard handle information coming into the Starship? Well, there's one way of doing it is this sort of everyone reporting to the captain. So it's sort of a bit cut off here, but it says damage report down the bottom, right? Captain Picard's sitting down and it goes around the room because all of these other people on the Starship, right? Wesley, Data, Riker, Thingos back here. They've all got different responsibilities and they're looking at different control panels for the sensors. And so he'll say to Wesley, you know, what's going on with the long-range sensors, and Data would be looking at the short-range sensors, and you know, etc. So he's looking around the room asking everybody for what the information is, and that's good because he'll get an overview of the whole state of the whole ship. Is that always how we get information on the Starship? There's obviously another option, which is a general kind of plot point in Star Trek Starship Adventures, which is that there's some kind of emergency, right? And Riker has to lean over and say, look, Captain, there's something important happening right now which I really need you to look at. And of course, in that moment, we can ask whether Captain Picard is really in charge, right? Of course, he's sort of nominally in charge because he's the captain, but his attention is being taken by Commander Riker without him sort of giving it away. He hasn't asked Commander Riker to have information. Commander Riker has just said, look, there's information right here which is so important, I know you're going to want to know about it, so stop what you're doing, please, and come look. And I guess if we potentially take this analogy too far, we have to ask the question that what happens after, right? So there's some information which is coming from Commander Riker, and maybe, you know, it's a Romulan attack cruiser or whatever we have, and we have to do a lot of work about this information, and maybe it's nothing. And either way, once we've handled that information, the control of the Starship then would go back to the normal flow of operation. Back to Commander Picard in charge, Captain Picard in charge, and everyone is doing their job. So the question of this lecture is, when we're on our disco board, how do we get from your CPU being in charge to some other thing being in charge for a little bit, just enough to handle the interruption, and then how do we get back? Now we can look at these two styles of, these two ways of getting knowledge, two ways of getting sensor information, as two different styles of handling communications. And this one, the first one, where he's going around the room asking everybody what they're up to, we could call that polling, right? So the CPU, or the program in charge of the Starship or the computer, is going to go around to everyone who could potentially be giving us information and saying, okay, what's on long-range sensors, what's on short-range sensors, what's the engine status, what are the weapons status, getting all the statuses, and now we've got all the information. And this other style where someone else can temporarily take control, do everything they need to do, and then we return back to our normal operation would be the interrupt style. So these two styles, polling and interrupts. Okay, we can call the analogy time over for the moment and look at what these might look like in some kind of imaginary assembly programs. Just make sure my my question. So Gabe in the chats just said, alternatively, Captain Picard might have set up a set of preconditions under which Riker, or however you spell it, is permitted to interrupt him. And that's exactly what we're going to talk about. Under what circumstances can something else interrupt the CPU's flow of operations in order to contribute important information? So here's the first idea. Now, we're going to check each external device at a certain time, and we'll need to do this regularly. So you know all about like the main function in your program, right? That's the first function where you get to write some code in your disco board. We call it main, and many systems have this concept of perhaps a loop in the main function that just goes over and over again doing certain things. So we got our main label, and then at the end we go back to main and we just do that in a loop. So our main function here is going to do some important work. But first it's going to check the keyboard, check the mouse, check the camera. Yeah, we get to do some actual work there. And each one of these would be some other imaginary function. And then we might check the USB, check the temperature sensor, do some other work. Yeah, we get to do some work. And then we got to check the USB again and check the network. And then finally we get to do this all again and keep going around this loop. And within this loop, which are the lines of code where we get to do work? Well, we get to do our actual important computer work here in this function, and we get to do some other important computer work in this function. But every time we go around our loop, it may take quite a long time to do all of these things. Check keyboard, mouse, camera, USB, USB 2, network. We'd have to work out how long that takes and make sure that this is acceptable. So this is a polling idea. Let's look at our other idea for interrupts. So in this part, maybe just looking at the code first and then we'll read the text. In this part, we've got our main loop, but we don't have any of that stuff about checking sensors. We've just got our two functions. We're going to do some actual work and do some other work. So now our main function is much more compact. And then our checking of the keyboard is going to be in some other kind of function called an interrupt handler. So we might, just for example's sake, we might have our keyboard interrupt handler, which has its label there. It does what's needed to check the keyboard, and then at the end we BXLR out of that function. Now the trick here is that in order for this to work, there needs to be some signal that comes from our keyboard. Whenever someone hits a key on the keyboard, that signal needs to get into the CPU to say, instead of doing whatever you're doing here, you can no more work on doing actual work. I'm going to stop you there and take the program counter out and instead go into this interrupt handler for the keyboard. Okay, and then there might be some other thing where if there's a network message waiting, we might have another handler, right? Our network handler or something. Net handler. So the sequence of code, the clockwork sequence of fetch, decode, execute going through the CPU is going to stop when the CPU receives this signal from the keyboard. It's going to stop. And the CPU is going to automatically branch down to a function that handles this interrupt. And we call it an interrupt handler, right? Because it's going to handle interrupts. Now, this is not something that you can do without hardware specifically designed to do it inside our processor architecture. So if our processor always proceeds to the next line of code that's loaded in the program counter, and that can never be stopped, you can't have interrupts. We need to have some part of the CPU which can alter this sequence of code going through. And what might that be? We're going to find out how this works in practice in a minute, but just before that, I just want to have a look at maybe a CPU architecture kind of guiding diagram. I think you might remember this diagram. We looked at it in, I think, week 2, which is going back a fair way now. It's going to come back more and more in the rest of the weeks before the end of the semester. We kind of go in this full circle thing in COMP2300 where we start off with thinking a lot about CPU architectures and how ALUs work and how digital logic works, and then get deep into assembly language and many topics, and then we come back at the end with some more about CPU architectures. Anyway, my point in bringing back this diagram is to know where an interrupt is. These are question marks, by the way, they're terrible question marks. Which part of the CPU architecture should be affected by an interrupt? And in fact, what it is this thing called the sequencer, which is going to line up instructions that are loaded from code, decoded in the decoder, put into a sequence, and then sent out to the ALU, sent into signals into references to load certain bits of data, right? So this is where our assembly instructions are actually getting kind of directed out to the right bits of the CPU to be executed. So after it's executed an instruction, it might have to check every time and see, hey, wait a minute, is there an interrupt? And if the CPU can do that really quickly, or just very efficiently have some method for tracking down whether an interrupt has occurred and which one has occurred, then we can have this elegant way of dealing with our external information. Why is it elegant? Well, it takes out, it's elegant because we get to remove all of our manual checking for each of these things, each of these external components, and put them into a separate function. And each of those functions is then sort of automatically called by the CPU at a lower level than our actual program logic. Now, just to be clear, there's good reasons to do the polling method as well, right? It's not like on a Starship, the captain never goes around and asks everyone what they're up to or what the status is of their sensors. There's always a balance between these two methods, but the interrupt ones are actually crucial. I should note that, like, for many times when you're implementing something on a microcontroller, for instance, if you've done any sort of fun projects with Arduinos or other microcontrollers, and you wanted to check a sensor, well, probably the easiest way to check a sensor is going to be doing some polling. Very simple to implement. Someone's just asked a quick question. I don't know what, someone's asking a very complicated question. Soft IRQ is level triggered as a state assigned via OS changes, whereas hard IRQ is edge triggered, such as polling the IO write stream. Well, I don't know what that means. I'll have to think about it. Someone else in the chat maybe can open up a discussion about that. Let me go back to the polling versus interrupt topic. So with polling, of course, devices need to wait their turn, but it's very easy to implement it because you can just add all these checks into your while loop, into your main loop. And it's also possible to calculate, for instance, the latency very precisely, because you might know exactly how many lines of code there are between doing your work and checking each sensor. So if you wanted to really have good control over how frequently you checked sensors and how frequently you updated that information, polling is definitely the way to go. And it's certainly fastest for a small number of devices. E.g., if you're writing a program for a microcontroller like a disco board, you just want to check one sensor. That's all the program's going to do. This is going to run very quickly and efficiently. Someone's asked if we're using interrupt program to diagnosing external interference. Is it for maintenance? Interrupts are not for maintenance. They're for normal operations. When you hit a key on your keyboard, that's an interrupt. When you click a button on your mouse, that's an interrupt. So what we're getting to is this idea that if you want to get any information that's unexpected into your CPU, you have to use an interrupt to do it. And this is where we get to the downsides of polling, why we can't use polling. Because if you have the very long main function, if the main function's gotten unmanageably long, having to check every single sensor, you might not have time to check every sensor, or you might have too long a time between checking a sensor to actually catch a very short event. So if I was checking the keyboard first, then doing a long amount of work, and in between that amount of work, someone had pressed a key on the keyboard and their finger had come up again, by the time I'm checking the keyboard again, well, the signal is gone. So the only way to capture that signal in a timely manner is to have an interrupt send it. You also need interrupts for timer-driven actions. If you have anything which needs to happen on a regular schedule, you can set one of your timers up on your disco board, and the way they communicate with your CPU is to send an interrupt. You can use this for transient hardware interactions. Transient meaning it might be short in time. That means it's something like a keyboard strike where someone is pressing the key in, letting it go. So that was short in time and now it's disappeared. The only way to capture that is with an interrupt. You might also like to schedule some action in advance, preemptive scheduling for something. If you say, I really want this to happen in 5 seconds, then you can set up your timers and use an interrupt to do that. I guess from the programmer's perspective is that you do need to have a little bit more, you do need to put in a little bit of work to set this up. This is certainly the case in assembly. You have to do some work to set interrupts to work correctly, which we'll go through in a little bit. And it does require some hardware, right? Our CPU has to have this modification so that when an interrupt is detected, the sequencer stops, loads it. It's not like you need to look at all your CPUs and check whether they have interrupts. They all have interrupts of certain sorts now. Like the first experiments with interrupts were in the 50s, so we've certainly included this technology in all subsequent CPUs because they're so useful. Now well, maybe not. There are some weird CPUs that don't have them, but we'll discuss that at a later day. The interrupts are crucial. This is how we get information into computers broadly, if it's something transient like a key strike. And in fact, starting next week, all of your labs and assignments are about interrupts. So this is why we have a whole lecture on them, even though it's somewhat of a nebulous concept right now. All of your labs and assignments are about use interrupts. So why is this important? And what are the challenges here? Well, so far, your disco board has been running like clockwork, fetch, decode, execute, fetch, decode, execute, fetch, decode, execute so far. And today we are smashing that assumption because an interrupt could happen at any time, anytime. An interrupt could happen at any time. So what does that mean for your assumptions as a programmer? I'm going to keep an eye on the chat, sort of thinking, knowing that it's about 30 seconds behind, so I guess I'm going to talk amongst myself for a few seconds while someone might come in with a thought about what this means for your assumptions as a programmer. So far, we're really when I ask what your assumptions are as a programmer, the question is about when you're programming something on your disco board, how do you know that certain things are going to be the same as they were when you come back to it? When you call a function, how do you know that your information in your register is in the same place? When you load some information from memory and you store it back, how do you know that things in memory haven't changed while you were gone? So this is a really, really important assumption, and it's something we're going to be unpacking this week. And I did ask a question in the exam about assumptions as a programmer, and the reason was that I want you to start to consider, or I expected you to be considering this already, but I want you to continue doing it from throughout this course. What parts of the program are you in control of and what parts aren't you? And in interrupts, you're certainly not in control of the interrupt handlers, or you're not in control of some of them. And the bit that even when you are in control, as in you have written them yourself, you're not in control of when they occur. And that means that, for instance, you don't have the ability to do any setup for your interrupts. If your interrupt has been, it's just a function which is getting called by someone else, you might have been in the middle of some important work, all your registers are full of important information, and then this function just suddenly gets called, and we have no idea how to kind of understand why we're in that function and when we're getting back and whether we should have packed up our work before we got there, right? We don't actually have time to pack up our work. And you know that we had those caller save registers, callee save registers. So the caller, we're not even the caller. The function is just it just happens. So we don't have time to save those caller save registers. And this is going to be a bit of a worry, right? Because our assumption is that we're in control of calling functions, and that whenever we call a function, we get a chance to kind of pack up our workspace so that the function can do its work. And then when it comes back, we can set our workspace back up the way it should be. And at this point, this assumption is broken. So no one's really answered my question, I suppose. But yeah, there was an important question from the chat about whether timer interrupts could be used in assessment 2. The answer to this is yes, they could be. The second answer is we don't expect them to be, and it's not going to be it's a little bit complex to work out how to do that, and I don't really advise you to try it unless you know what you're doing. The timer interrupts are crucial for assignment 3, however, so you'll get your chance to play with them in this music making sort of scenario. The reason is that a timer interrupt is used by the part of the code which sends the audio to the headphone output, that play audio sample function. So if you start using the timer interrupt for other stuff, the main timer, then you might find that you've messed up the timing for the audio output. So you just have to understand how that works, and we don't expect you to do it at this point. Now, we're going to move on to the next topic. I think there was a bit of discussion about this very difficult question from Jackson. Oh boy, I mean, my fear is someone in a lecture asking me a question I don't understand, but it's also fun to understand, do some research and get back on these things. I think Mitchell in the chat is on to try to figuring out what's going on, but perhaps we can understand a bit more about these interrupts that Jackson was asking about in future. So the big picture here, interrupts, expecting the unexpected. So our computer needs to respond to external events all the time. Keyboard presses, mouse clicks, opening the lid, closing the lid. Your disco board has a little keypad on it, this thing. And if you want to respond to that, the best way to do it is with interrupts, because this could happen at any time. Another thing we need to respond to is errors, and interrupts are used for that as well. Sometimes we call the kind of interrupts that's caused by an error an exception instead, but they can sometimes be handled exactly the same way from the perspective of your software. Interrupts happen all the time, so it's not a case that these are a rare events that we only need to handle in emergencies. They happen all the time. You're always tapping on your keyboard, interrupts are going into your CPU 24/7. Maybe you're not using your computer 24/7, but they're always happening. Interrupts break our assumptions about fetch, decode, execute, so we need to follow a process, some kind of procedure to save our context and then get it back later. What do I mean by context here? Well, that's all the stuff that your program is doing which makes it your program. Where you're up to in your code, what your registers are, what your stack state is like, what the flags are like, right? You might have been in the middle of a compare operation, or you might be in the middle of an IT block, right? With all these flags set in this particular way. And if some other program function jumps in and starts doing stuff, how are your flags going to be correct when we get back? Now this is where we get to the next topic, which is how does an interrupt work? What's the procedure? How do we store this code, and how does our disco board know how to get to the code and then get back again? It's more complicated than functions now because we're not in control. Some automated process has to help us out to make this work. So we've got a little story, the story of an interrupt. Here's the pre-interrupt state of our disco board. And we've got some code here. And then we've got our handler function, which is already set up. Okay, so that's starts with, a label, ends with BXLR. That's what, as I said before. And our disco board is just ticking along with this code. Everything is fine. Fetch, decode, execute's ticking away. We've got some stack state, right? The base of the stack at the top of memory. And here's one stack frame. A frame meaning like all of the stack information owned by one function. And then that function has called another function, so there's another stack frame below that. Some parameters for that function. It's context that needed to save before starting, return address, local variables, etc. So we're all happy, everything's going along. Now let's see what happens when an interrupt occurs, right? We're about to stop everything and transfer control to the handler. So the first thing that happens is when this interrupt signal gets fired, the CPU does some work for you to make sure that you can get back to where you were before. So the first thing the CPU does is take your program counter and the flags and save those on the stack. CPU does this for you. Now the program counter has been set to your handler code, right? So it's at the start of the handler, and it's ready to run down this handler and do the work it needs to do. And the PC, program counter, and the flags have gotten stored handily for you right on the stack. And at this point, I want to mention this now. We'll get back to why it's important later, but the link register here, the link register, which would normally, if you call a function, the link register would point to where we were supposed to go next after we come back from the function, right? But in this case, the link register doesn't have that information in it. It has a special value. Special value. Okay, we'll see the reason in a minute. Someone's asked a question in the chat. So would interrupts have their own calling conventions, e.g. not use registers 0 to 2, since we don't have time to save those values for ourselves? That's a very excellent question. We're about to see exactly the answer to that in a minute. The question is they don't have their own calling conventions. It's actually cleverer than that. They've got normal calling conventions. So now our next step of our interrupt story is that the handler code is going to do some stuff. It's going to behave as a normal function. What do normal functions do? Well, they push the callee registers onto the stack. They may declare some local variables, and then they're going to do some handler stuff do some input-output, run some time-critical code. Maybe you need to make sure that a sample comes out the disco board every 48,000th of a second, so some timer would be ticking through and doing this important job. But the primary thing to recognize here is that this is just a normal function. Pushing registers, declaring local variables, this is all normal stuff. There's no change to the calling convention here. We've just put some stuff on the stack and we're just going to behave as normal. PC's in there. Now, of course, when we're writing an interrupt handler, one crucial thing is that one important consideration is not to let it run for too long. We generally like a interrupt handler to be short so that the other parts of the program don't notice too much that we've left them for too long, right? They might notice for too much if they come back and it's like 20 seconds later and some semi-time critical code has taken a long time. Another example is if you're using your laptop and your keyboard doesn't work, right? You get very annoyed, or your mouse is locked on the screen. The control of your interrupt system hasn't been returned from some other process. It's a bit more complicated in OSs, but basically the wrong part of your computer has control and it's not giving it back. And when you do get it back and your mouse goes all over the screen, you're like, oh, stupid computer, throw it in the bin, get another one. Maybe it's not the computer's fault, it's probably the software's fault. Now, the final part of this process is that the handler is going to clean up after itself, just doing its normal, or the second final part, is going to do its normal function cleanup, remove its local variables, pop registers. Now it's right at the end. And the last thing it's going to do is BXLR, right? And if we had set LR to where we would normally expect LR to be, which is down here, then of course we would get back to our previous location, but our flags would still be on the stack, and we might have messed up those call or save registers, right? But I said before that the calling convention was the same for an interrupt handler. And that's because of this special LR value. So when we do return from interrupt, BXLR, the special LR value is telling the CPU that we're returning from an interrupt, we're doing this one specific time-limited operation, and I would like you to put everything back the way it was, and the CPU goes and automatically takes all this stuff off the stack, puts the PC back where it wants to be, puts the flags where they're supposed to be, also deals with the callee registers R0 through R3. They go back off the stack. I forgot to put them in the diagram, but they were in the stack there somewhere automatically from this interrupt kind of procedure. Clever, hey? So this is how it works on your disco board. Control is transferred automatically to a handler, and then to simplify matters, the CPU automatically deals with cleaning up this the calling convention stuff that the caller would normally have to do. So I've got a slide here which has this whole timeline just in text, but it's the same text from those previous 4 slides. So I won't go through it quite right now. Now, a few things to consider before we go into more detail about interrupts. We'll start to look at it practically. A few things to consider. Can interrupt code also be interrupted? Yes, it can. In fact, the interrupt system on the disco board's CPU allows you to have interrupts within interrupts, which is sort of illustrated in this diagram down here. So maybe interrupt number 1 was triggered, we're in regular execution. This is our line of regular execution. When interrupt 1 was triggered, we ended up in the handler for interrupt 1. Then interrupt 2 happens, we end up in the handler for interrupt 2. then finally interrupt 2 is able to return, goes back there, and interrupt 1 goes into a handler there. Hoping for some comments or questions while we're going through this slide, because we've got a few minutes just to cover these things to consider. And if you have something to consider, now's the time to pop it in the chat and tell me about it so we can try to address it together. Another question is, which interrupts are more important? Can you set it so that, for instance, maybe you don't want interrupt 2 to be able to override interrupt 1 because interrupt 2 is less important than interrupt 1. This one's very important. It can't be interrupted. If it is, the whole system's going to break down, the plane will crash, the Starship warp core will overload. So that interrupt really has to be handled, and interrupt number 2 can wait. If that's the case, we can set interrupt number 1 to have a high priority, and we can set interrupt number 2 to have a low priority. And if that was the case, we wouldn't get this. In fact, we would get, when we return from interrupt 1, we would be allowed to have interrupt 2 take control. So the interrupts can handle in a nested way or happen sort of in order. So that's handy. Now, we were discussing about how interrupts put stuff on the stack, right? So if we take the concept of interrupts putting things on the stack and we combine that with the concept of interrupts nesting in between each other, can we then have a stack which gets so large that it overruns all available memory, right? If you put your finger on the keyboard and you hold it down, or you get your disco board button and hold it down, is that going to just fire an endless stream of interrupts and immediately overrun the stack with these handler codes that are just storing useless information? Well, yes, it could. That's a big design consideration. And for this reason, sort of because interrupts are unexpected, they're messing up our expectations as to being able to predict precisely what is going to happen in a computer in the future. So if we're trying to verify that a stack will never be overrun, then this could be a problem for us. In practice, this is not something which tends to happen too much in normal situations, unless unless the system has a kind of poorly designed piece of software running on it. You're unlikely to be able to do this on the disco board, because if you held your button down, all of the interrupts would be at the same priority level, so they would not interrupt each other. They would just be in sequence like this, and the stack would only get overrun if they can nest within each other and go up and up and up and up and up. If they can go in a sequence like this, we can certainly prevent other stuff on the board from running, right? If you can hold down this button and it just keeps firing interrupts and never gives control back to the main loop of the program, then our program stops doing the important work which we designed it to do. So that's another problem. Yeah. Someone asked, if the memory is near full memory and there's an interrupt, how would the system handle this? I think it would just crash, yeah. You would, on your disco board currently, I mean, we could probably do some kind of experiment to find out exactly what happens on a disco board if you're in that situation. Like by putting the stack pointer, if we set the stack pointer to be at 0x2 followed by 7 zeros, so the bottom of memory of SRAM, and then we called an interrupt on purpose, we could be in trouble. Maybe we'll try that later. So another question is, can we have a do not disturb sign? So this code is too important, I don't want to do interrupts. You can choose to ignore interrupts of certain priorities, and there are some interrupts that can't be ignored. So we generally call this masking, when you've got an interrupt coming in, and if you mask it, that means you don't pay attention to it. but there are some levels of interrupt that are not maskable, so they can't be avoided. For instance, actually when you press the reset button on your disco board, this button resets the CPU. That's an interrupt. And that one you can't avoid. If the reset button gets pressed, the CPU will reset. Other kinds of interrupts that can't be avoided are ones related to an error, right? If your program can't continue, obviously we can't avoid that one, so it's not maskable. Okay, I haven't seen any other questions, but if anyone pops one in, we can certainly get back to it. Oh, there was another one. Someone asked, what happens if typing a second key is typed before the first one's interrupt is over? We don't want the second one to be registered first. Well, and if that was the case, that would only happen if we were allowing the second key to interrupt the first one. And in what I was suggesting would be the correct, or a better design would be to have those interrupts handled in order. So that's certainly a consideration. If you have one message coming in, you're dealing with it, and another message coming in, are you going to end up dealing with the second one first, out of order messages? But in an interrupt context, I think we can handle this by just dealing with them in order. That means that the first interrupt handler blocks the second one from occurring before it starts. I just said blocks, and that means that we've run into the first time in which we have to consider asynchronism in our our disco board programs. Which is a sort of an exciting time, right? We're now not considering, we can't just consider our program execution happening as in order in the code in memory. We have to consider what events might happen and the time they might happen, and will that result in our program being broken or not broken? Yeah, I mean, Gabe is giving me some information about keyboard scanning matrices. I was sort of oversimplifying to some extent the keyboard analogy, but if we just think about this as a button, if you had two buttons and they were directly connected to interrupts, you could have this situation. My suggestion would be that they should have the same priority so that they would block each other. Is there a limit to the queue of interrupts? I don't think the queue is maybe it's not gonna work exactly that way, because it can't queue them up. It's just not gonna fire until you handle it. So I guess potentially if you took too long, then your second interrupt might have actually disappeared by the time that you get to it. We'll have to work on understanding that one a bit more in depth. Maybe on the next lecture this week, I'll have a good answer about that one. Oops, I don't want to be in full screen mode. No. Why it doesn't work with the pen in full screen mode, but there you go. Big picture here, interrupt handler is a function. You get to write it. That's what we're going to do now, but you don't get to choose when it runs. So that's the cause of all of these issues. Oh no, press the F button again. Okay, so now we're going to talk about interrupts in practice. Interrupts in practice. Oh, sorry, these early mornings get my throat all blocked up, so I have to sip a little bit of water while we're doing the lecture. Now, even though this is the first day that we're discussing interrupts on your disco board, most likely you've already experienced at least one interrupt. And the specific interrupt I'm referring to is usage fault. Now, why would you have experienced usage fault? Well, if you've ever found yourself in the infinite loop on your disco board, then that's actually because an interrupt has occurred and your disco board has stopped running your program and put you into this handler so that it can keep running on something. All the CPU wants to do is clock over and over and over again and run like clockwork. It needs to have something to run on. And that's what that bit of code is for. It's just a landing place for it to go when it doesn't know what to do in its program. Everyone in the class probably has tried that thing where you're putting .word, putting random memory information into the instruction stream, .word in the code area. And if you try to execute one of those instructions, the CPU doesn't know what to do, it interrupts itself, or it causes an exception to end up in that area. And we can sort of see that when we go into where is our infinite loop? Here's this one, infinite loop, and it's also called default handler. So that's the, well, I'll make my text bigger so everyone can see. Default handler is the handler function for like many interrupts that haven't been set up yet in your disco board. I'll show you more in this file a little bit later. So how do we configure an interrupt on a disco board? Well, we want to use one, and first of all, why, but we'll discuss that in a minute. We need to enable the interrupt, which involves doing some operations with the disco board hardware. We need to define the handler function, and we've got to make sure our hardware is all set up in the correct way. You've started to understand how to set up hardware on your disco board when you've been doing experiments with the LEDs, right? You had to enable the hardware which talks to the LED, then you had to get the hardware to turn the LED on and then turn it off, right? So that took a few lines of code just to get those little memory addresses and everything organized. And it's can be a little bit complicated, but at least it's a set procedure. So the handler function is the bit which is actually going to deal with the interrupt when it's called. So we're just going to talk a little bit about that. When your CPU on your disco board experiences an interrupt, it may, unless we're in a very simple CPU which only has like one thing that can be interrupted, we have to choose which handler function to go to. And so normally we've got what's called interrupt vectors, or an interrupt vector, which is a set location in memory, which has the address of each interrupt handler function listed. And if your CPU knows it needs to go to interrupt 0, then it goes to the first one. And in this case, on the ARM CPU, that one's called reset handler. So it knows that these are words in memory, each one's a memory location. They're kind of set out in an array or a vector, and the CPU can just index through them to find the correct interrupt number for the number that it knows it has to go to. So in our case, on the ARM Cortex-M4, there's hundreds of interrupt numbers. You can have lots of interrupts. And they all have to have an address in memory, but they're not all set up to do anything. So you might have noticed when you look at your run programs on your disco board that you have code in this weird file called startup_STM32L476. We had a look at this before in some of our experiments. We're going to have another look now. You might have ended up, particularly when you ended up in the infinite loop, and been really confused and thought, how am I ever going to understand any of this code here? Unfortunately, we're now going to look at it, so you do have to understand it, haha. But you understand a lot more about assembly programming now, so I think if you look at it, you'll see what is going on. Here's our list here's our vector for our interrupt handlers. First one, reset. Second one's NMI, non-maskable interrupt. Some other things, hard fault handler, mem manage handler, bus fault handler. So many kinds of interrupts that are high badness, I guess, or they're important for the way that your disco board operates. This thing's called SVC handler, supervisor call handler. We'll talk about that in our operating systems lecture. Debug monitor. And then there's many other stuff. Now we're getting into things that are to do with external hardware. This one's called XT, external interrupt 0, interrupt request handler. So there's 5 of these ones right here, which are interrupt lines just for external hardware. And then other things, direct memory access, I2C, these are to do with handlers, timers, so all of this stuff. And there's heaps of them. Wow, they go all the way down. Loads of them. Now, so far, all of these ones are linked to the same default handler. And our job when we're defining an interrupt is to actually just override the default handler easily. And in this case, we want to be doing an external interrupt. So we're going to override the XD0 interrupt request handler, which means we just have to write a function with that name. And all you have to do is just, as a basic kind of outline for it, you have your label, the there, and then you have your BXLR, the back again. It's important in this context to have a sort of correctly set out function, having the type directive function and having .global. The reason that is that the linker needs to find your version of the XD handler and sort of understand that that's supposed to be in place of that word, that label in the other file, the startup file. So the linker has to sort all these things out. You have to give it correct information. If we look down at how this XD0 handler is dealt with now, that's a label to somewhere, so we can find it. Here it is, and it's actually just kind of got this .weak, a weak reference to the default handler, a default label. So this is all these are dot words. That means they're directives for the assembler and the linker to know what's going on in your files. They're not things which the CPU will ever see. By the time the CPU gets it, XD0 IQ handler will be replaced with a memory address. So it just needs to be, you need to be giving these instructions for the assembler and linker to put the correct memory addresses, make sure that it has the address for the handler that you want to be giving it. By the way, you're going to definitely be doing this in next week's lab. Lab 9 is all about interrupts. Lab 10, wouldn't you know it, that's all about interrupts too. And in fact, labs 11 and 12 are also highly related to interrupts. So you're going to be getting plenty of practice. And oh, by the way, assignment 3, all about interrupts. So get used to these ideas now, particularly in next week's lab. I want everyone to be putting a really good effort into that lab to get the handle of this concept early so that you can understand the more complicated use cases later. So what are we going to do with an interrupt? Well, suppose I want to use the joystick. I've got my little button here on the disco board. I want to just be able to click it and for something to happen. Isn't that similar to activating the LEDs, right? So with the LEDs, you were going into looking for these hardware things, the AHB to enter to enable the correct bits in that, and then that would enable communications over the disco board's hardware buses in order to activate that LED, and then if you could talk to the correct register in the bus related to the LEDs, and if you set that bit to 1, then it would turn on, and if you set it to 0, it would turn off. So can we do that with a joystick? I mean, I guess we could, because the joystick is memory mapped in the same way as the LEDs are. And you can just go in and find out if look in a register and see if some information is high or low. But the idea is to get this to happen automatically, and that requires a little bit more effort on our part as programmers. So if we just think about where the joystick is in your disco board, this is a little bit of a complicated diagram, but this is the STM32 microcontroller. That's the big chip of your disco board, right? And this chip includes an ARM Cortex M4 core as its CPU, but it also has extra bits of hardware. So when you're dealing with these interrupts, we have to start to understand that there's different bits of hardware in your disco board have different kind of locations within the CPU architecture, and some are inside the Cortex M4 core. They're part of the ARM basic design for that CPU, and some parts are outside. And in fact, our processor core this thing has interrupt stuff built into the basic Cortex-M core. The first bit that's important is this nested vectored interrupt controller, NVIC. That's the bit which actually handles which interrupt you go to. And we've also got this important timer, sysTick. That's the most important basic timer on your disco board. That's the one which we use for making sure the sound works coming out the headphone output. So it's one that you don't want to mess up if you're doing an assignment, although in your labs you will be experimenting with messing it up on purpose just to find out how it works. It's always good to break things to find out how it works, isn't it? So you can learn valuable lessons by breaking it. Another important bit of hardware is this controller for the external interrupts, which is another little bit of hardware, another module, which is actually outside the Cortex-M core. They're in the STM32 microcontroller. The XD controller is connected to this bank of wires on your disco board called GPIO. That stands for General Purpose I/O. And in fact, we've got several banks of these, and this one's GPIO Bank A. And then on the disco board, each of the Bank A GPIO controller has many pins. So these are all pins along the edge of the disco board. You might have looked at those and said, oh, I'm never going to have to bother with those. Now you do. Some of them say things like PA0. That means port A, pin 0. PA5, port A, pin 5. PA1, port A, pin 1. And then there's another one, PB3, port A, B3. Some of these pins are used for other stuff at the same time. Some of them are available for your use, or they're all available for your use, but you might disable something else if you try to use it. So a little bit of care is required. But even though we've got PA0 as a pin right here, it's that one, it also is connected directly to this button. So when I press down on it, boop, that causes an interrupt. So the question is, we have to configure our disco board to get the message all the way in here to the processor, all the way through these different things. And we need to, unfortunately, interact with all of these different parts of the CPU to set it up to do what we want. This is a little bit fussy. There's 8 steps. We have to enable GPIO-A, enable the GPIO port, enable the sysconfig piece of hardware. So the clocks for those need to be enabled, or they need to be connected to the processor clock. We need to set PA0 to be an input, not an output. It's a general purpose input-output, so it can be either input or output. We need to set it to input and then activate its pull-down resistor. That's a bit kind of abstract at this point, what a pull-down resistor might be. But if you've got just a pin dangling, a loose wire dangling outside of your CPU, there could be static electricity or something making very small changes in voltage on that, which could actually be detectable by the CPU. So a pull-down resistor is a wire connected to it with this electrical component called a resistor. And that, just to draw a little diagram, you've got there's the CPU. Here's your wire dangling around in the wind. I don't know what's going to happen to it. It could have little bits of static electricity. So we have a resistor connected to ground, and that means that if there's not like a voltage with some guts behind it, like someone pressing down a button and connecting it to the power supply on your board, if there's no significant current, the voltage on this line will be 0 because this resistor and connection to ground will pull down its apparent voltage from the CPU's perspective. And then when this is turned to 5 volts by connecting the battery, the apparent voltage there will be 5 volts. So this means that our disco board can actually detect a change of voltage on that line reliably. Then we've got to set PA0 as a source, the source for the XD0 interrupt. We've got to enable XD0 interrupts and set it to be a rising edge trigger. What does that mean? Well, if we're looking at the voltage on that line, it would start at 0 volts, and then when you connect that button, I guess it could go to 5 volts or 1 volt. I've forgotten what the voltage is, or 3.3 probably, 3.3 volts. And our interrupt controller can be looking for this and say, oh, that's an interrupt. I need to do something. You can also set it to a like falling edge trigger in case you have wired your electronics the other way around. It doesn't mind, it will do both. And then finally, you just have to enable XD0 interrupts in the nested vectored interrupt controller, because the interrupt controller is the one that's actually going to talk to the CPU. You have to tell it what the priorities are of these interrupt lines and which ones are allowed to proceed. So let's do it. In fact, I've already done it because it's a pain. I provided this code for you. This is actually also provided in next week's lab, but I thought we just might have a little look at it. If you've tried the lab this week, you might see that we're entering a bit of a different phase of our labs in COMP2300, where we give you some other source code files. So far, you haven't gotten any files other than the main.s, which has nothing in it. But now we've given you this LED library, simple LED library that turns LEDs on and off. It basically does the work of labs 5 and 6, or helps you understand how to do that. Does all of these settings for you. We've also got a little utility library which sets up many little addresses for you from the disco board, so you don't have to look in the reference manual for everything. And it also has a couple of handy dandy functions like set bit that lets us set a particular bit in a base address with an offset. The bit index is given as another argument, so you can set up some hardware a little bit more easily. Clear bit, same idea, but the opposite. And toggle bit, turn it on or off. Yeah. Now in my program, I've already set up these 8 steps. So first things first, interrupt the GPIOA, enable the GPIOA clock. Similar to what you were doing in labs 5 and 6. You just have to find the base address for the GPIOA in the memory map. Has this label RCC_AHB2NR. So this is the reset and clock control component of your CPU. And this is a section in the disco board reference manual, which you might want to have a look at. Things get complicated at this part of the course now because the manuals just get so massive. If you didn't like the ARM instruction reference manual, you definitely won't like this one. This one's 1,700 pages. It's just crazy. The most important pages in this manual is like where it's actually telling you what the memory map is for your disco board CPU. You can find out where all the peripherals are stored and what they're supposed to be doing. So this is the memory map of the peripheral area. Has these 2 buses. One is the peripheral bus and the high performance bus. And there's 2 of each kind. And all of your peripherals are connected into the disco board in those 2 buses. And then if you wanted to get a GPIOA's address in the high performance bus, you can look in here to find the details of exactly how that works. Oops. No, it's my thing. I want to follow that. I won't do it. Oh well. Yeah, but I've done this all for you in this example. So first of all, we're enabling that GPIOA clock in RCC, one of our peripherals. Then we're enabling the clock for the sysconfig component or module. Then it says in the manual that after you do that, you're supposed to have a little bit of a delay so that everything can kind of settle down electrically, so your sysconfig module knows what it's doing. So the delay function, basically just has a bunch of knops in it to run your CPU through a couple of cycles. Now we set pin A0 to be input, so you have to use the GPIOA mode register. That's also set up in through these memory mapped addresses, and you have to give it a 2-bit instruction about the mode. So you can use this copy bits function to do that. Then then we set PA0 to pull down, set the pull down resistor. Another change in the GPIO-X pull up, pull down register, or GPIO-A pull up, pull down register. Actually, for most of these, you can type GPIO-A because our util file has all of these addresses handily listed out for you. So if you know what memory mapped register you want to talk to, you can just type in its name. Really handy. And we do a sort of an inline offset right now. Haven't had a question in a while. Everyone's just blown away by these wild ideas so far, I suppose. Then we set up, or we turn on the interrupts for XT0. Then we set it to rising edge. And then finally in the NVIC, we enable XT0's interrupts. So now my interrupt is all organized. Finally, we did it. And then in our handler, I haven't done much in my handler except kind of give it its addresses, but I'm doing one thing, which is that when the interrupt comes in, it sort of sets a bit which says that a request has been made. And when I handle that request, I should unset that bit to say that I'm clearing the request. So we're kind of telling the NVIC that we've done the bit of work that we were supposed to be doing. So far I'm not actually doing anything by handling the interrupts, but I've at least set up my handler. Now the question is, how am I going to find out if this works? So if I run my program, uh-oh, something bad happened. It worked before. Oh, come on. Unplug your disco board and try again. Probably because I pushed a button. Well, that's bad. What did I do that was wrong? Oh, that thing. Someone's going to tell me. Yeah, back to the number. What is it? OX. I have this on my website, so I wouldn't forget. I shouldn't have been so tricky trying to use the other thing. Well, I'll make sure it works for you later, but this is on the website, so you can have a look. It's also just in the library for Lab 9. Lab 9 has this in the library, so you can check that out of that code. It's not like it's a secret. Okay. Hopefully Harrison will delete this from the video when he edits it for me. Maybe. At least I got one audience member. I know that Mitchell's there keeping me honest. Okay, so if I run my code, then things are just going. And how do I know when an interrupt has occurred? If I press the reset button, like, that's it, right? It's just, how am I going to know? I could pause it, and I'm just in this end loop. I'll try to pause it right after Nope. See, the interrupt is handled so fast that even if I clicked these at the same time, I'm in the wrong area. I want to somehow stop in the interrupt request handler, in my XT0 handler. So I'm going to put a breakpoint in there so that when I click this button, I should end up inside that location. Okay, now we're running. I'm going to press continue, so I'll run my program continuously. It's more useful to be pressing this continue button now when you've got programs that have like I/O from the actual board, right? So you can press continue and then see something happen when you click the button like this. Whoop, I'm in my interrupt handler. So I actually managed to do it with this code. Get inside my interrupt handler and get some information there. While we're in our interrupt handler, maybe we could have a little bit of a look at what is in our register, our link register. So if I go down here to LR, you can see it's got a funny number, OXFFFFFFF9. So that doesn't point to anywhere in our code memory, right? Our code memory was right down the bottom of memory in very low addresses, and that's a super high address right at the top of memory. So that's one of our special values, our special value for LR, which means that when we try to return from that, the CPU is going to set everything back the way they were. Now I might just do a little bit more excavation here just to see what's happening, because I want to know, I want to prove to myself that if I'm doing work here in my program, do some work, that my work is not going to get messed up by the interrupt. So if I just put some numbers in the I'll just load some stuff into some registers. Letter R0 equals OX dead beef. Letter O1, OX8 bad food. Letter R2, OX cafe beef. Letter R3, OX. So we've got some stuff here in my working registers, and I want to make sure that these are getting put away when when my interrupt fires. So I'm going to do that by having a look on the stack after I get my register, my interrupt to fire. So here we are, running our code, going along in our loop. And then suddenly, bam, interrupt fires. We're out of our loop and we're in the interrupt handler. LR is set that way, and my stack OX2001-7FDC is set to a certain address. Now, what I might do is just have a look in memory at an address just before that. A little bit tricky to figure out an address in memory when you don't know what you're looking for, but I suppose I can get 256 bytes. So I'll start at 2001-7F00, and I'll look for FF bytes. So it'll take me through a bunch of stack all the way up to where it stops. So you can see the stack pointer is at FDC, 17FDC. 17FD. Whoop. There. So you can see I've got all of my dead beefs and Cafe 2300 all put on the stack. So the interrupt system, the NVIC, has done its job and saved all of my important information onto the stack. You can see it starts about there, right? There's dead beef, ate bad food, cafe beef, in little Indian format, of course, Cafe 2300. Yep, so we can be sure that we're doing our job, that it's doing its job. So how does this affect your assumptions? Well, you know, thankfully, when we call a handler or a request interrupt gets called, we're not relying on some other colleague or yourself to have written your function correctly so that it packs up all of the context that you might want to save. It's built into the CPU to do that, so you don't have to worry about those caller save registers being saved and restored. So that all works perfectly. It's designed as part of the CPU. You do have to implement your handlers correctly from the perspective of the callee. They have to make sure that they're doing their job with respect to R4 to R11, the callee save registers, sorry. If you're going into another function like I do here, going to set bit. You have to make sure you push LR and pop it again right at the end before you pop back out. But other than that, right, our life is made very easy by this system. And one cool thing about it, because handlers are just normal functions, if you wanted to call them yourself in your main loop, of course you can. You can just type the name of that function, BL to it, and use that in a known way rather than an unknown way with the interrupt routines. So that's very handy. I think I'm going to stop here because it's now 10:36. And we're also at the end of the lecture. I suppose I just want to mention that I've put in a bunch of further reading about this stuff. Probably most importantly is the Intro to Computer Organization with Raspberry Pi book has a chapter on exceptions and interrupts for some important background information about this. There's also some information on a couple of books on O'Reilly.com. I found out that if you're an ANU student, you can look at learning.o'reilly.com for free. So they have lots of great computer science textbooks you can check out there. These are chapters from a book called Essentials of Computer Architecture, which would be a typical kind of textbook for this course. And also a couple of extra bits of information on YouTube and 6502.org for understanding how interrupts works on different kinds of CPUs. So maybe with that, I'm going to go to the outro. I don't think there's any more. You can ask me more questions in the chat if you have them. Otherwise, see you folks on Friday. Have fun with the labs this week. I'm really glad that you folks were out there. I was a bit worried when we got to the long interrupts demo that I was going to lose a few people, but it's good that you guys stuck with me until the end. It's certainly a little bit, it's a bit of a procedure. I don't think that there's any way to put it with these interrupt things. Configuring them yourself is an annoying procedure. And I wonder, because I didn't make the notes for the labs, and I wonder who it was who wrote down the original like joystick.s. There's a joystick.s library which does this setup procedure for you, and you use it in your Lab 9. I wonder who figured it out originally, and whether they figured it out by reading the manual or by reverse engineering the C code which sets up the interrupts that comes with the disco board, right? It comes with a library written in C for interacting with these hardware things. Yeah, I think it was Ben Swift as well. I wasn't sure whether it was Ben or one of the other tutors. But I have a feeling that maybe it just had to be reverse engineered from the hardware abstraction layer library. Of course, it wouldn't be too hard to reverse engineer. Like there would be some C function which says set up joystick, and then it would have basically exactly this line of operations. Exactly this line of operations, but written in C instead of assembly. And then you're doing the same thing in C. You're just writing to generating a memory location and writing some information to it using logic bit wise operations. I think this is one of the things I never got into in Arduino stuff was actually doing interrupts, because it's a bit of a pain to get set up, and it was a bit abstract. It feels a bit more abstract if you're in a higher level programming language. I guess in Arduino, in C++ in general. If you're in this high level programming language, then to suddenly start dealing with a bunch of strange memory locations that have weird words, all capital letters, XD0 IRQ handler. Like, what is that? So it's a bit difficult to get into that, but so all of my Arduino experiments where I've used sensors, I think have ended up being using the polling function, but that wasn't too much. It wasn't too bad because they never had to do very much. I used to make a lot of little microcontroller things for art projects and performance projects. So if anyone's interested, you can stalk my website and see all the kind of weird stuff I used to get up to in performances. Okay, I might call that time to go. So catch you team on Friday.